Hey there guys, Beans Brother here again. Now let's talk about magnets and a little bit of their fields. First we'll start off with a description of the lab and fundamentals. We'll then talk about lab setups and lab results, and then finally we'll do Glowscript Code and explanation with some final questions. Here on the introduction we could say that our end goal is basically to use a bar magnet to describe and record the transfer of magnetic fields, where you could visualize it on the top right in the slides. We're going to use the Biot Savart law to calculate the magnetic field along with the distance dependence equation, where the magnitude is expressed as kr to the nth power. For n we got at the end negative 2.950 meters and the magnetic dipole of 3.206. Field calculations are shown over here, where as we take this iPhone that we have and use an app, we'll measure out all the distances that are shown here along with plotting them on the graph. For the distance dependence equation, all we simply did was take the distance dependence equation in the top left and the Biot Savart law below that. Combining them together, you'd eventually get the magnetic dipole, which is equal to 10 to the 7th kr to the n plus 3 power, all division by 2. When we graph it, in the form of y is equal to mx plus y naught, we get ln of this b magnitude on the x-axis is equal to n ln of r plus ln of a k. From the graph, we could see that n is equal to negative 2.950 as our slope, and ln of k from the y-naught intercept as negative 14.26. Therefore, after plugging it back into our magnetic dipole equation that we solved earlier, we get 10 to the 7th times our k value that we just solved times r to the 0.05 power, all divided by 2, giving us our magnetic dipole of 3.206. So for the lab results, we see that when the magnometer is far away from the magnet, it measures near zero magnetic fields. And as the magnometer moves closer to the magnet, the measured x component of the magnetic field increases. The vice versa is not true, so the closer that we get, then the magnetic field would actually increase. And as the position of the magnometer, yes, it does have an effect on the measured x component of the magnetic field. Now time for some Glowscript. Alright guys, let's quickly review. First, initialize a magnet object. Go ahead and initialize all of your constants, the most important of which is the magnet mags and the hat direction, along with the OBS axes right underneath that, so that we could go ahead and set some vectors. The magnet.mu is just going to be our previous mu hat and mu mag that we solved for earlier. Here's a quick definition for our functions that we'll be using later for the magnetic field. This for loop basically says that I'm going to run this twice, and at the end I want you to flip these field directions in the negative direction but keep the same orientation, so that way we basically copy and paste our arrow forwards a little bit, because if you think about it, a magnetic field could just be replicated on both sides equally and oppositely, but in the same direction though. For our for loop, we're just going to initialize the first half. We're going to say that we have an r-axis that's going to equal to our observation axis. We're going to go ahead and refer to that r-axis instead of our magnetic dipoles kind of functions to go ahead and recall them and calculate for a magnetic field in each. From there, just make a arrow that points in these kind of axes by some scale value. And then again, just go through your if loop and do the same thing, but for some position negative distance instead of positive distance. Copy and paste really if you think about it. Then we're just going to go ahead and print our x, y, and z magnitudes, get our distances, and get our magnitude at 45 degrees. Now let's run the program. Now, as we could see over here, it's about what we expect, with the magnetic field coming out and back in. However, in this green arrow, I really want to put some emphasis on it. This is the 45-degree angle, and at the bottom we see our magnitude that we'll compare for our real-life example now. Alright guys, so for our observed and our theoretical numbers, where on the right is theoretical and on the left is observed, we see that they're definitely different, but on the bright news though, we have gotten it down to the same magnitude, which is very, very good for just experiment versus reality. So that's pretty good application of the laws, I'd say. For our final questions, we'd have to say that what if you hadn't oriented your experiment to compensate for magnetic north, and had instead angle it somewhere else, what would change? We oriented it to x to account for the magnetic north to calibrate for 0t, but if we orient it incorrectly or differently, then we would not have it set to 0t Teslas. What if you had two identical magnets together end to end, and you just did your experiment again? What would you think? I would say that the magnetic field calculations would definitely increase, but it may not necessarily double. Now, you guys have a beautiful day, because that's pretty much it. I'm gonna go ahead and go to sleep. I hope you do too, and have a wonderful life.